Hi, this is Ms. Fitzmaurice, and this video is about situations in which energy is not conserved. So by the end of this video, I want you to be able to identify situations in which the energy of a system is not conserved. And again, that's going to depend on how you define your system, which objects you're keeping track of. I want you to be able to distinguish between heat and work, and I'll define those in a little bit, and set up equations to solve heat and work problems. And that's actually what we're going to focus on in class on Monday. Alright, so far we have been dealing with situations in which energy is conserved, so we've been using this equation. Sigma E naught equals sigma E. Okay, so all the energy at the beginning equals all the energy at the end. Now, this equation is always true if your system is the whole universe. But it's kind of hard to keep track of every object in the whole universe in order to satisfy this equation. So I'm going to give you an example of a situation in which energy is not conserved for the system. Okay? So again, this equation is not always true for systems of a limited number of objects. And here's my example. I have a person, okay, so say there's a hill, okay, and I have a person, and that person does not walk up the hill, but they're in an elevator, and they're at rest initially, okay, and then the elevator takes them to the top of the hill. So this is time 2. And then they're going to get out of the elevator, and they're going to maybe slide down the hill on a sled. Okay, and so they're sliding down. On a sled, and eventually, say they have some velocity right here, eventually their sled comes to a stop. Okay, so I have a bunch of different time frames, and I want to look at what energy is present at each one of those time frames for this person. Okay, so in our very first situation, really we have no gravitational potential, we have no kinetic, so if we're only looking at kinetic, gravitational, and spring potential energy, we pretty much have nothing here. Okay, in our second time frame, we definitely have gravitational potential, as we do in this third time frame. Okay, now our person has slid down the hill, they have kinetic energy, and then there must be friction on this hill because they come to a stop and they have nothing at all. Okay, so in this situation, energy can't be conserved for this person because conserved state means stays the same, and you know, if you have 0 and then you have something that's not 0, the total amount is not staying the same. Okay, so in general, energy is not conserved for a system when a force is applied to the system, and I'm going to say applied to objects in the system because it can be an internal force. So a force is applied to objects in a system over a distance in the direction of motion. Okay, so if we look back at our situation, okay, we had the elevator, the normal force was pushing up on our person, and so we had a change in energy right here. Okay, as the person was moving downwards, they always had friction, okay, and that friction changed the energy of the system. Okay, the two forces we don't count are the forces associated with potential energy, so we don't count spring or gravity forces. Okay, having potential energy is kind of like counting that change in energy in the conservation of energy equation. Okay, so there are lots of situations in which a force could change the energy of the system. I want to distinguish between two different types of forces. And I'm going to call them useful and useless. And these two different types of forces change the energy of a system in different ways. Okay, so useful forces, I'm going to define them as forces for which the direction is specified. And I'm going to say must be specified. Okay, so examples are like a push, pull, tension, normal force, okay, that sort of thing. Useless forces are forces that always act against the direction of movement. So examples of this could be air resistance, friction, if you were moving through the water, like F drag from water. They are always slowing you down, okay? Useful forces, so like a push or a pull, could be doing either one. They could either be slowing you down or speeding you up. They're intentional. Okay, and what we say is we say that useful forces do work on an object. And that's the technical term, is work. Okay, and the equation for work is that the amount of work done, the amount of energy added or taken away from an object, is equal to the size of the force that's parallel to the direction of movement times the change in distance. So we have F parallel times delta x. Okay, and so this F parallel is the force or part of the force parallel to the direction of the movement. And the delta x is the distance over which the force is applied. Okay, and of course work is the amount by which the energy of the system is changed. Okay, so I'm going to give you two examples, and I want you to try to follow along and calculate the work. Okay, so my first example is a box which is sitting on a hill with an angle of 37 degrees, is pulled by a tension force of 200 newtons 10 meters up the hill. Okay, so you might start thinking about the angles and trying to find FGX and FGY. We don't need to do any of that because we want the work, and the only force, as long as there's no friction here, okay, the only force parallel to the direction of movement, because this right here is the direction of movement, is our Ft. So our work is going to be F parallel times delta x. In this case, we have work is equal to 200. Okay, we don't have to do anything with that number because it is already parallel to the direction of the hill, times our change in distance, which is 10 meters, and work is change in energy, so the units have to be in joules, so our work is 2,000 joules. Okay, so that was our first example. I want you to try to think about our second example. Now this is a top view, and say there is a ball on a string and it is moving around this circle. Okay, let's say that the tension force is equal to 200 newtons again, because I'm lazy. And let's say that the radius of this circle is equal to 2 meters. Okay, I want you to try to calculate the work that the string does on the ball. Okay, so go ahead and do that and then check back for the answer. And the answer is that this is kind of a trick. Okay, the reason this is kind of a trick is that work is equal to F parallel, and that's parallel to the direction of movement times delta x. Now say this ball moves around in a circle, you could say the delta x is 2 pi r. Okay, that's the circumference, that's how far the ball moves each time it goes around. But the direction of movement is going to be always tangential to the circle. On the other hand, Ft is always going to be in towards the middle of the circle. Okay, so because these two things are perpendicular, F parallel is actually 0. There is no force parallel to the direction of movement. So even though this thing is moving around and around, the total work is 0. Okay, so the next thing we want to talk about is how non-useful forces change the energy of a system. And what we say is that non-useful forces cause heat. Okay, so examples of these non-useful forces are similarly friction, air resistance. Basically, they always slow things down. And the equation for heat, so heat is going to be represented by Q, and heat is going to be, because we're always losing energy from heat, negative absolute value of F parallel delta X. Okay, so again, this F parallel is the non-useful force, and delta X is the distance through which the force is applied. Okay, so I'm going to give you a couple examples. Okay, so my first example is that a ball drops through air. We say F air is, in this case, the force of the air is 0.02 newtons, and the ball drops a height of 1.4 meters. If I wanted to calculate the heat, I would use Q equals negative F air times delta X. And in this situation, the heat would be equal to negative 1.4 times 0.02, which could get me negative 0.028 joules. Okay, so that's my first example. My second example, I'm going to have both heat and work. Okay, so in my second example, I have friction, and I told you the force of friction is 6 newtons, and I have a pulling force and an angle of 37 degrees at 50 newtons. And I want to know what is the heat, what is the work, and let's say this box is dragged a distance of 10 meters. Okay, so hopefully you can identify first which force causes heat, which force causes work, and then I want you to try to solve for them numerically and check back. Okay, so our friction is going to cause heat. Okay, we're going to use Q equals negative F parallel delta X. Okay, in this situation, what that means is that we have negative times 6 times 10 meters, or negative 60 joules. F pull causes our work, but F pull is not F parallel. Okay, the portion of F pull parallel to the direction of motion is only going to be F pull X. So we have to find F pole x, and that will be F pole times cosine 37, and you should recognize this as one of our special triangles. It's a 3, 4, 5 triangle, and so the cosine of 37 times 50 will be 40 newtons. Okay, so for work, we have F parallel times delta x. In this case, that's going to be F pole x times the change in distance, which is 10. So we have 10 times 40, and so the work done will be 400 joules. Okay, and so when we think about how the energy of the system is changed, because the heat is negative, we say that friction took 60 joules away. And I'm going to just write FF took 60 joules from our system. Okay, and that taking away is because of our negative sign. The work was positive, so we say that F pole added 400 joules to the system. Okay, so now the last question is, how do we set up energy problems where there's heat and work? Because I'm not just going to ask you to calculate the heat or calculate the work, but if there's heat and work, how do you calculate final height or final speed? And the answer to that kind of comes with just the general idea that heat and work are equal to the change in energy. And so we can write that out. So we can write that out as an equation. And it's actually just like it sounds. We have heat plus work is equal to our change in energy. So we have Q plus W. We know how to calculate both of those are equal to the change in energy is like delta sigma E. Okay, and we know that delta, or change, is final minus initial. So we have Q plus W is equal to sigma E naught minus, final minus initial. So sigma E minus sigma E naught. And notice, if there is no heat or work, we just have a 0 on the left-hand side, and we would get conservation of energy back. So on Monday, we're going to try to solve problems using this equation right here. This is the most general energy equation. And to figure out what to put into these, it's just like a conservation of energy problem. You have to go through and figure out, do you have kinetic energy? Do you have gravitational potential? Do you have spring potential? Okay, do you have those things at the beginning? All right, so I will see you on Monday. And again, in class, we'll be trying to solve problems using this last equation.